we saw at the end of the last theory class that we could decompose a unitary acting on the d-dimensional complex space into d choose 2, or roughly d squared, order d squared, two-level unitary matrices. So I wanted today to start with an example, and then what we're going to do is, once we've got our two-level unitary operators, is show that those can be implemented using Toffoli and a single qubit unitary operator with a control, so a controlled one. And so that's going to be our first objective. But first, let's start with an example. So here's an example of a 2-qubit unitary operator, and we would write this like this, just to indicate that the operator is acting on the 2 qubits. So this is a 4-dimensional. So this is a unitary on 2 qubits. So this C2 tends to 2 is C4. And I more or less made this up randomly. Oops, that's not good stuff. Where's my one? So I'm going to write down how this unitary operates on 2 qubits. And it takes, this is what it does to the computational basis. And in matrix form, this would be the matrix. So let's just see, the general order we use is this order. So the image of the first basis element will go in the first column, so we would end up with 0. Here we go 0, 0, 0, 1. Here we've got 1 over root 2, 0 minus I over root 2, 0, and finally minus I over root 2, I over root 2, minus I over root 2, 0. So apparently this should decompose into, at most, 6 two-level unitary. I think I made a mistake this last. So this doesn't correspond to that. Here I have root 2, so when I wrote down the matrix, I have 2. So I hope I haven't messed this up. Let me just have a quick calculation. Where do those come from? That times that. Okay, I think these should, this one here and this one here should just be 2s. So it doesn't really matter. So this is then equal to this decomposition into two-level unitary matrices. So two-level just means that they all but 2 rows, square rows and columns, it looks like the identity matrix. Here you see we have a little Hadamard stuck where the first and the third should be. It's been replaced by a Hadamard. Here we've got a Hadamard at the top. And then the little identity matrix down here. So that's replaced the 1, 2. And here we have 1, 0, 0. And you can check, if I didn't make a mistake, that this product of 4 two-level unitary matrices does indeed decompose into these 4. In this case, it'd be 4 were enough. Okay, so we saw an algorithm in the theorem how to, when we proved that this was the case, exactly how to obtain this decomposition, or a decomposition. Now, how would you implement this two-level unitary operator here? So that's the first question. And I claim that this is implemented by the following gate. So this should be a kind of controlled Hadamard on the first qubit, but it's controlled. So what's happening here is 1, this is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. So we've got the Hadamard going on the first qubit, but being controlled by the 0. Not by the 1. The 1 doesn't get control. So if I just did this kind of gate, this would say if the second qubit is set, then apply the Hadamard to the first qubit. But that's not the case. We want to apply the Hadamard to the first qubit in the case we've got a 0 in the second. So we simply put a NOT gate here, and then a NOT gate afterwards. And now that effectively means that we apply the Hadamard when this is not set. Okay, when it's a 0. Okay, so the 0 goes to a 1 here, then we apply Hadamard, and then we switch it back again. Okay, so this is given by this circuit here. Do you see that, or do you want me to do that explicitly? I'll calculate that.
No, it's fine for me.
Sorry?
It's fine for me.
Okay. And so how would you do this one then? So this is now a Hadamard here. Do you see what's happened here? So it should be Hadamarding the second qubit when the first qubit is not set. So this should simply be this one upside down. Well, maybe I just got lucky here, and there were some nice. These Hadamards happen to fall into nice things. This one, for example, is slightly more tricky. Well, it's doing something. Actually, it's probably not. So it's doing something on the first qubit when the second qubit is set. And what it's doing exactly is a C naught, so an X and then a Z. Okay, so or roughly an IY or something like that. Okay, so that's probably not too bad. What would be difficult is if we had, what would be more tricky was if we had a matrix which would have an identity matrix in the middle and then something here. So how would we implement something like this? It's a two-level unitary matrix. So our idea is going to be to prove in the first part of the class today that we can implement these two-level unitary operators using just single qubits and one controlled U, where the U is on a single qubit operator. Okay, so that's going to be our challenge for today. I'm going to start just by looking at this general thing and seeing how we can implement this. I'll leave that up there for a second. Before I do that, of course, we already saw that the unitaries we could break down. So once we've done that, so we get down to our unitaries, we can then break down the unitary into the decomposition of the rotational matrices. So we saw before that U can be written as e to the I alpha RZ beta RY gamma RZ delta. So we proved for any single qubit unitary U. So if we do that now if we wanted to do this entire thing, so we would then have this in the first, sorry, well, the other way around. That's got to come in the qubit first, so the other way around. But anyway, we more or less see how to break down these 4 two-level systems into a control U and some X's, and the U's we can do into further decompose our U's into then. So in this case, I worked out an example for you of this H, and H decomposes as e to the I pi Ry of pi divided by 2 Rz of pi. Okay, and you can check that this is this is cosine divided by 4 minus sine divided by 4. The y1 is the classic rotation. And then Rz pi should just be minus I0 I. And if we multiply all that out, then we should get H. This I we can take over to there. Here we get 1 over root 2, 1 minus 1, 1, 1. The I over there gives 1, 0, 0, minus 1, which brings the minus down to where it should be, down here. Okay, so that's how we decompose our Hadamard. So we prove then that the controlled Hadamard that we get here, or we do here, then decomposes further into single qubit operators. So this controlled H here is equal to single qubits and some C naughts. So I'll just write B here. Tell you what B is in a minute. Where these single qubit operators A and B are, A is Ry pi divided by 4, and B is Ry. This is minus 110. Okay, so that is all I've done there, is I have decomposed the unitary operator H is as in the theorem that we did in the last theory class, and then I use the fact that the control U is then equal to this single qubit operators with the C naughts. Okay, so this was our C in our thing before. And this was our e to the I alpha. Okay, so that's just an example of the theorem that we saw last time. So you see that you keep going. So you have to substitute the first controlled, so the two-level unitary with this controlled H here, controlled U here with some other single unitaries, and then the control itself breaks down into single unitaries and C naughts. So you've got a whole thing breaking down to a whole load of single unitaries and C naughts. So let's have a look again at this one, because this one's not so obvious how to implement it, and it will give us a good indication of what we have to do in the general case. So as we saw before, sometimes we want to control with the 0 and not with the 1. And when we do this, we put an x before and an x after, and that way the 0 goes to the 1 is set, and then we have the C naught applies. But we just, as notation, we can't write this every time, so we just write this like that. Okay, so I'll be trying, this is by definition. Okay, so being not set now is going to be an open circle as opposed to a blank circle. And what I claim is that this matrix here is implemented by the following circuit. Which way around is it? Yeah. Okay, so we're just going to verify that this indeed allows us to implement this kind of weird one where there's no obvious, it's the 0, 0 and the 1, 1. So there's no obvious bit that it's acting on. Right, so the normal way of checking that this works is to see what happens to 0, 0 if we, and all the computational basis elements if we apply this circuit. Okay, so let's do it. So we start with 0, 0, and we hit a controlled C naught, but a controlled by the 0 and not the 1. So it's controlled if it's not set. Well, this isn't set, so this is now going to go to 0, 1 on the first bit, first gate here. Now it hits this, and this is controlled by a 1, and it says apply this matrix, this single qubit unitary operator to the first qubit if it's set, and it is set. So 0 goes to the first column, which is the A and C, so this will then go to A0, 1 plus C 1, 1. And finally here, then if it's the first one's not set, then we C naught the second one. So this then goes to A naught naught, and this one's set so nothing happens to it. C 1, 1. And as if by magic, the 0, 0 has gone to exactly his image in the first column. Okay, so now we can check the other two, the others. So very quickly I can do 0, 1. 0, 1 is set, so this thing goes to 0, 0. But this is now not set, so nothing happens to it. And then here it gets back. This is not set, so this thing goes back to 0, 1. And likewise with 1, 0. 1, 0. This is set, so nothing happens here. This is not set, so nothing happens here. And this is not set, so nothing happens here. So that just flies straight through the whole circuit untouched. And finally, 1, 1 goes to not set, so nothing happens. 1, 1. Here it is set, so we apply the unitary, which goes to B0 plus D1. And now not set, so if the first qubit's not set, we switch it, so this goes to B00 plus D11 as desired. And as with all things, just checking these things just becomes second nature with a little bit of practice. Is that clear? I can't see anybody today, so it's a little bit.
Yeah, it's clear.
Okay, thank you, thank you. All right, so now we're going to see a slightly more difficult case. Let's try and do the same thing now, but let's imagine that we have a 3-qubit system. How would we go about implementing a 2-level unitary operator So let's take, for example, so the let U be 3-qubit a 3-qubit 2-level unitary. And let's make life difficult for ourselves. So U is going to be it's going to take the 0 zeros to the 1 1 1s. And on the rest of it, it's just the identity. Okay, so for every, this is now running through the rest of the elements in the computational basis. So that's a 2-level unitary operator, and we can apply this again. And the idea is that we've got to get from zeros, we want to push everything onto the same qubit, and then apply our unitary operator, which will be the simple A, B, C, D. Yeah? So let's just let U hat be A, B, C, D. So we want to try and push everything onto the same qubit in such a way as we can then apply U hat. And, well, possibly not obviously, this we can do in the following way. And I think once you see one more example, it's the kind of thing which suddenly is going to become fairly clear. At least I hope so. Okay, so this is going to be control down here, control with a 0 here. And now we could topically controlling the U hat. And now we get back in the way. Right, and the idea here is that these Toffoli gates will only flip something in one of the qubits. Okay, so whatever kind of Toffoli you have, there is only one one qubit which is going to be affected by these, and so we can effectively we're going to try and get everything as 0, 0, 0 and a 1, 1, 1 onto the first qubit, so they look the same. Well, they both want to have 1, 1 if we're going to have here on the second and third qubit. Okay, and you can see that this is what this is going to do here, right? So 0, 0 comes in. Zero, zero comes in, and he gets switched here to 0, 0, 1. And now we've done it, so this is a 0 and this is a 1, so this then gets applied the C naught here, so it goes 0, 1, 1. And now, when we get here, you see, we've got both of these two things set. So we apply the U, and we get the A and the C as before, A, 0, 1, 1.
Right. If you have empty circle and like a filled circle, it's like the product of like that particular column, like with this, just adds third plus not the first, or
no. So this requires both the first two to be unset. Yeah, it requires 0 to apply C naught to the third.
Okay.
It requires a 0 here and a 1 here.
Oh, okay, okay. Yeah.
So you can have any combination on your, and then well, I'll talk about this in a minute. So this gate will do nothing unless you are 0, 1, 1, 0, 1, T, and then you'll go to 0, 1, 1, 0, 1, T plus 1, modulo 2. Yeah?
Yeah, thank you.
Yeah. And everything else just stays the same because it doesn't have all the control sets correctly. So this thing goes to A00 plus C111, and then it gets repaired again back here. Yeah. So now we have, if you have the 0 and the 1, then you'll get your second qubit flipped. This other one does not get affected, and now if the first two are set, you flip the third, so you get back to 1, 1, 1. Isn't that clever? And then the 1, 1, 1. Well, the 1, 1, 1 sails through all the way to here because same. And then here the 1, 1 is set, so now we just apply to the first qubit and we get a B0, 1, 1 plus a D 1, 1, 1. And now And now we do have the 0 and the 1 in the first term. So we go to the B0, 0, 1 plus B1, 1, 1. And we do have 0, 0 here in the first and second qubit. So this then gets sent to B0, 0, 0 plus B1, 1, 1. So everything fine for these first 4 terms. And now anything else going in, that's not true, is it? So now we have to check the others really. So, I mean, we'll just talk through it. I'm not going to write anything else down. I mean, if you have now 0, 0, 1, that will get sent to 0, 0, 0 here and then get put back to 0, 0, 1 at the end. There's no other way of applying the U. That I think we can see. Yeah? There's only 2 ways to get there, and that's either starting from 0, 0, 0, which then gets sent to 0, 1, 1 before hits this gate, or the 1, 1, 1. Anything else is not going to have these last 2 things set. And then, so this is then clearly the identity, okay? Because this is the inverse of this, and this is the inverse of this. So how does this work? How does this work then when we have n qubits? So I think, or another maybe another three qubits, but with some other 2-level unitary operator. Well, the idea is if we have, so if U is only non-trivial on, let's say, x1 to xn and y1 to yn, then with a let's call these things, I don't know, generalized Toffolies, yeah? Because we're allowed to, instead of just taking the control, we can also take the control on 0. So then with n-gate generalized Toffolies, we can step by step to take whichever one we want, y1 to yn to y1 x2 to xn. Then apply a single cube, control U hat, where U hat is a single qubit operator. On the first qubit. Where down here on the n-1 other qubits, you have exactly x2 to xn either controlling it, yeah? So exactly if x2 to the xn are all 1s, then these would all be black dots, and wherever you see a 0, you put a white dot. And then it just applies it to these 2 cases, and then you just copy whatever you got here and do the inverse on the other side and put it all back together again. Is that clear? I mean, if you really, really want to try and write it down formally, it's a little bit ugly, but I think you can see that we would need at most n of these things, right? So, and we need less than n. In fact, it's then minus 1 now of these n generalized topics. Well, it would be 2, of course, because you need to undo it at the other end. My pen is running out. Now, at this point, when I first started preparing this lecture, I then went, oh, well, it's fairly clear that you can then implement these n-gate generalized toffolies with n C-naughts, and that's not actually true, even. And so I just want to just explain to you that this is actually kind of quite a difficult problem. So how many toffolies do we need to implement this? Now, at some point, we saw that we could implement a toffoli with a constant number of single qubit and oh no, we will see, sorry, we will see an exercise, what was that, an exercise 2, that you can implement a toffoli, so that would be with controlled 2 things here and an x here, with just single qubit, in fact 3 single qubit operators and 2 C-naughts. But what about the general n one that we got like here, for example? Well, it will be, as I say, it will be exercise. Let's see if I got it. Yeah, so in exercise 2, we will prove that this is equal to where v squared is equal to u. So then here we have only single qubit, here we have a controlled single qubit operator, which we've already seen we can break down into single qubit operators and C-naughts. That's what we did last time. And so here we have some more C-naughts and some controlled single qubit operators, which means we can implement a doubly controlled u, and if u is x, this is toffoli. So if u is x, then this is toffoli. Okay, so we know that we can break down. So what was it? Each one of these would have been into 3 single qubits and 2. So that's 9, 11, something like 12 single qubit operators and similar number of C0 gates. So what we need to do is see, can we break these things down into toffolis? Okay, so I want to see if we can break this down into a linear number of toffolis. I can make this.
Wait, the dots on like the last wire, we didn't draw them, or how do they work? Like on the last V, it has like a line above it.
Oh, sorry, it's here.
Okay. So wait, and it's not controlled by the second one. Like if there's no dot, that's what it means, right?
There's no otherwise that would be controlled by 2 of you. Which we're trying to break it down into single control.
Single, okay.
Yeah, because we already dealt with single control. So I can change this to these 2 black dots by putting x's here. Yeah, because remember the x will just flip the 0 to the 1, the 1 to the 0. So it's enough to be able to just do the ones where they're all black. Yeah. So this, using the exercise, we have that. So now let's just assume that we have all blacks. And let's add a few more just for good measure. Okay. So this little toffee at the bottom, we can break down using this. Okay, so we can just leave all those ones on top and say that this is equal then to something. Yeah. So this is going to be the little thing at the bottom, and then we've got 2 of those things going on. And now all of these are then controlled as they were before. And this final one, these are controlled by here, and this final one is then got to be, since this is controlled here, is now controlled by all of them. Yeah, so this is then all of these. So it looks like now, so I thought, oh, that's it then, right? Because now I've gone down from n to n-1 controls. So this would be like an n-1 control. So this we would call Cn-1, let's say x, because if you wanted to put a u here, then this would be the case u is x, yeah, because it's a bit flip. And so we've now got down to Cn-2s. Yeah, so this is a kind of Cn-2 here. But we've got 2 of them. So if we continue just like, okay, we'll apply this iteratively, then we're going to get an exponential number. Okay, so that's not good news because it's not necessary. What happens now is you can just draw these down here. Doesn't make any difference. Just to indicate the fact that actually, although you've got Cn-2, you've got an extra bit down here that you're not using. So you can now make use of this extra bit and implement this Cn minus 2 in the following way. So this Cn minus 2 with the wire that you're not using, your qubit that you're not using, so there's no dot here. This is now, let's indicate that like this. This is another Cn minus 2. And we can break this one down in the following way. Roughly take down n upon 2 of them here, then put the other ones down on here with a C naught here. Do the same thing again here, and then put them back down here. So I'm trying to make the big black dots as big as possible so you see where there isn't one. And kind of to prove this kind of this works, what you do is you kind of imagine, well, you imagine first that everything is set. Okay, so just to, I think there's, yeah, no, that's right. So imagine everything is set. What we want to do is flip the last, what we're hoping is that if all of them are set, these n minus 2 are set, then this last qubit will get flipped. Okay, so that's the plan. If everything is set, then this one will get flipped. Ooh, hold on, how's it work? Yes, I'm missing some dots here. Yeah, okay. Okay, so if everything is set, then this one will get flipped, which means that now these are all set. If this is, yeah, so whatever happens here, we want this to be flipped, right? So if this was, let's take the two cases, let's say this was 0, then these are all set, this is set, it gets flipped here. Now this one gets flipped, so this is no longer set and nothing happens here. Whereas if this one was 1, it would get flipped here, this wouldn't do anything, it would get flipped here back to 1, and now they're all set and it gets flipped here. Okay, so this is kind of a working bit. So this is a work bit. So if they're all set, so if all these are set, then this last one will get flipped, whatever the work bit is. And now you kind of have to argue, and it's not too bad to see that if one of these is not set, then nothing happens here and nothing happens here. If all these are set, then you flip it and then you flip it back again. And now you do the same argument top and bottom. And then if you don't have anything set, if you have something that's not set here and something that's not set here, then clearly everything just flows through. Okay? Was that more or less clear, or should I go through that again? Adrian, what do you think?
Yeah, can you please do that? Like before we had the cross was at the second to last bit, but now it's at the end, or what's the relate between the after the first equal sign, you sort of have these two drawings, and they're the same. The cross, the sum is at the end.
Yeah.
And before it wasn't. It wasn't at the end.
Yeah.
But there's no problem? Or...
Okay, let's start again. So I'm trying to break down the Cn minus 1.
Yeah, okay.
First things, I'm using exercise 2, in which you're going to prove this, to actually show that I can break them down to Cn minus 2 gates. 2 of them.
Okay.
Okay? And now take the Cn minus 2 gate apart. So this is now Cn minus 2. Okay, I'll forget about the rest of it. The rest of it's fine. I've now got to prove that I can do a Cn minus 2, well, I knew really, but of x, because I've got this v here. Well, then I have to reapply this again, I guess, for the last one.
Like, why do you need to go to the Cn minus 2? Can you just like split it in half at the beginning? And like compute if the first half is all set, and then add it to the second if the second half is all set?
Because I don't have a work bit here.
Oh, okay, and okay, so you need like an extra wire.
I need that extra wire. If I allow myself an extra work bit, then an extra qubit, then yes, I could do that.
Okay.
So I'm just seeing how many gates do I need if I want to stick to n qubits. How many?
And what lets you get the work bit? Like, why doesn't it mess things up to sort of change that one bit?
I'm sorry?
Why doesn't it mess things up to like have that bit be flicked on and off as you will? Or like you do it, or you put it back as it was?
Yeah, this goes back to how it was anyway.
Okay, so like those two sums would be in between the V and the V dagger. So which goes back to how it was. Or
so, well, all I'm doing is I'm now taking this Cn minus 2, and I'm showing that actually now I've got this extra wire which I'm not using. This wire here is now this wire here, right?
oh, okay. Okay.
Yeah?
Yeah.
And now I've split this into 2, and now, yes, everything's going very well, because now I can split it down into basically Cn minus Cn divided by 2s, with loads of extra wires free. So now I've got one more stage to do, and just to show you that you can then break down this Cn minus 2 into single Toffolies, normal Toffolies. Okay? And this all can be done in a linear way. So let me draw one more bit, and then I'll just tell you the conclusion of all our hard work. Okay, so this actually isn't in Yeltsin Chuan. I had to go looking at a research article. I mean, it's quite recent. This is 2000. Well, let me have a look. I'll have a look for you. And if you want, I'll put a link on that tonight, because I think it's absolutely fascinating, and I think it's well within reach. It's not anything too spectacular. Oh, it's 1995. But anyway, it was. So finally, if we have a Cn minus n divided by 2, so if you had something like this, but you have lots of gates free, lots of wires free, 2, 3, 4, and plus at the bottom, then you can then implement this. Quite sure what the right number of wires now. then go back the other way and undo it all. And then this continues, and you have to then undo the one before. Almost there. Well, something like this. Okay, so then you basically get the same thing on the other side, shifted up. Maybe I messed that bit up. This should be. Yeah, I'm not sure. Anyway, so basically this then breaks down with the work bits. You can do them into single Toffolies. So in the end, this Cn divided by 2 of x breaks down into at most something like 4n. So if you have a Cm with m less than n divided by 2, then you get 4n minus 2 C2x gates, also Toffolies. So it's a linear number. So in the end, you get down to a linear number of Toffolies. So let's put all that together and see what we've got. Down to, so we have so we have a unitary on n qubits, breaks down into d choose 2, so that's 2 to the n choose 2, 2 level unitary operators. Now the 2 level unitary operators, they go down into roughly 2n minus 1 n gate generalized Toffolies plus 1 controlled single qubit. The n gate generalized Toffolies, they then break down into some big O of n single qubit, well, single Toffolies, and then as I said, Toffoli then breaks down by the exercise we just saw into single qubits, single qubit operators plus C naughts. The single qubit operator here also breaks down into controlled single qubit, as we saw in the last class, also breaks down into single qubit operators and a C naught. That was what we did when we did the U, yeah? The expression for the U with the A being the C. So putting it all together, I believe that this should be, but this is big O of n squared 4 to the n. So suffice single qubits plus C naught. Well, I think we all deserve a round of applause after that. So as I say, Nielsen and Chuang are a bit vague about how you get from the n-gate generalized properties to the big O of n single qubits. And I will put a link to that archive paper, and you can have a look at it. Right. So on to 4.3 finally. Is that okay? Obviously, that's not the ideal number. That's quite a lot of single qubits and C0s, but we've proved that any unitary on n qubits. This is a universal set, okay, for quantum computing with this number. Okay. What we want to show now, well, not quite yet, but what we will also show in 4.4, that these single qubits can now be approximated with just Hadamard's and T gates, okay, and the C0s. Right, 4.3, back to measurements. Okay, so we denote measurement in a computational basis by this symbol. Okay, so the principle of deferred measurement well, this states that we can always move the measurement to the end of the circuit. So we can always move the measurement to the end of the circuit and if we've measured earlier on and used that classical information, so when we measure we get a concrete bit, and if we then used it, that can be replaced by a quantum control operation. Yes? And any classical bit used can be replaced by a controlled quantum operation. So let's see an example. So our classic example here would be our teleport scheme. So how was that? So we had our file on the first one. And we somehow managed to get this to Bob by starting down here with a Bell state, B00. So this was we then did a C0. here, Hadamard. And then we measured. So then we measure the first two. So Alice measures these first two bits. Oops. Passing the classical information she gets from that down here. And is it x then z? Yeah. Yeah. So this is x to whatever the measurement result was here. So this is my M2. M1. Down here. And what we inducted down was then sorry down here. Okay, so that was the classic teleportation. Okay, quick question. This is the kind of thing now we should be given the stage of. So how do you make this Bell state if you just start from 0, 0? If I give you two wires, 0, 0, how do I make a Bell? How do I make this entangled state? Anyone? Oof. You see, this is the moment where you should be in the classroom, so I can see your faces and see if you really know or not, and I have no idea. I mean, you should be falling asleep at the moment. Things like Bell state equals Hadamard, C naught, fall asleep. That kind of thing should be happening. Okay? So if you have if you start off with 0, 0 here, then what's coming out at the end here is beta 0, 0, right? Because this gets put into a plus, which is 1 over root 2. I'm just checking 0, 1. The second qubit, so we get 0, 0, 1, 0 here, and then you see naught, so the 1, 0 goes to 1, 1. Okay, and we get, so this is h of 0 is plus, which is this. If you see that's a plus, unfortunately, join those up. Yeah, so I hope these kind of things should be absolutely second nature now. So here we have we've done this beforehand. We've already made our entangled bits. And if you remember, Alice had these first two and Bob had the third one. So Alice then applies C naught Hadamard and measures. And depending on the result of her measurement, she then passes this M2 and M1 over to Bob, who then either, if M2 is 1, applies an X, if not, nothing. If M1 is 1, then he applies a Z, if not, nothing. And out pops at the end size. So what the principle of deferred measurement says is that this should be the same if we simply replace these classical bits and move everything over here to the end. Okay, so let's see if that's true. So how would the mu one look like? Now we've got nothing there. We've got the C naught. Now we've got nothing there. This classical bit is now to be replaced with a controlled one. Okay, so this now is an X here, and then this with a control Z on the first qubit. And what should happen if we start off with psi here and beta 0, 0, that at the end here we should end up with phi, regardless of what happens in what's happening in the other two bits. Okay, so let's just check that. So I trust you can check back that this works okay over here. So I'm just going to check that this is now also giving us the same thing. So this we can say is A0 plus B1. Okay, so we start off with A0 plus B1 and 1 over root 2, 0, 0, plus 1, 1. So this is our initial state going into the circuit. We hit this C naught, and if there's a 1 in the first qubit, it's going to flip the second qubit. Okay, so this then goes to 1 over root 2, A 0, 0, 0 plus A 0, 0, 1. The B is now going to flip the second one, so I get B 1, 1, 0 plus B 1, 0, 1 after the C naught. We now hit a Hadamard. Oh, I'm not sure I'm going to have enough space. No. Well, maybe what I can do is once I've written it down, I can just flip the ones that then get flipped. Okay, so Hadamard in the first. I don't manage to do it so much easier there. How did I do it so much easier there? Well, let's just go. So this is going to go to, so now we're 1 over 2, because all of these are now going to get root 2's as well. This 0 goes to a plus, so that's going to be 0, 0, 0 plus 1, 0, 0. This is going to be 0, 0, 1 plus 1, 0, 1 plus B 1, 1, 0 minus, sorry, so 0, 1, 1, 0 plus 0, 0, 1 minus 1, 0, 1. Well, I'm going to need more space. So I'm now with this Hadamard, and I'm just going to group now the first 2 qubits together. So,
I got a question.
Yeah.
Why in the second step, the second term that is A001, it comes from A011, and why did you flip the second?
Yeah, thank you. I don't know.
Okay.
I don't know.
Okay.
No reason at all. So that then changes here, yeah? So that's a 1, and that's a 1. Thank you. I would have found that mistake in a minute, I imagine. So here I get 0, 0, A plus B, 1, plus 0, 1, A1, plus B 0 plus 1, 0 A0 and the 1, 0 here minus B1 plus 1, 1, and here I have A1 and then I get minus B0. Okay, so that seems to be correct. Well, and now, so this at this stage, it's the same as the 2. And now before what Alice did, if you remember in teleportation, is she then measures and tells Bob what to do. Okay, so if she measures 0, 1, she's here, and she says, that's the wrong way around, isn't it? If she measures 0, 1, I think that's the wrong way around. Oh, do we agree? Because Alice has these two qubits, right? If she measures 0, 1, oh no, then this is 1, so she applies x, which is right, yeah? And now if she measures 1, 0, then this is, she wants to apply the z, so this becomes a plus b, and then if she measures both, then she flips and then does the z. And here you see, so if you look over here, this is exactly what this does. Yeah, so continuing with the deferred measurement circuit, we have this goes then to 1/2 and a controlled, so we're controlling on the second qubit. So if the second qubit's set, well, let's just write psi here because that's just psi. So if the second qubit's set, as it is here, we apply an x, so we get psi here. If the second qubit's set, well, it's not, so we don't do anything. And if the second qubit's set, which it is, then we apply x, so we get a 0 minus b 1. And now when we apply the control z on the first qubit, we get 1/2 of 0, 0 plus 0, 1. This then goes to a plus b, so this then becomes psi. So we get 1, 0. Likewise here, so we get plus 1, 1. And the whole thing psi. So whatever happens, you end up with psi here. Well, you may ask yourself, why do we make such a fuss about this then? If we could have just done straight down with that circuit, is, well, here we lose all the teleportation idea, okay? There's no, this is just saying that you will get the same result if you defer the measurement and replace it with. So we now put measurements at the end here. Whatever we measure, we will, whatever which one we get here, we'll get psi in the third qubit. But of course, we lose the quantum, we lose the teleportation interpretation in the deferred measurement circuit. Yeah. Now, what we want to look at now is what happens if we want to measure in a basis which is not a computational basis. We've been spending quite a bit of time in the last chapter on measurements and problems and generalized measurements, and certainly one of the simplest things we saw was measuring with respect to an orthonormal basis. At the moment, we've only seen how to measure with respect to the computational basis. So let's have a look at an example of one of our favorite bases, the Bell basis. So here's an example measuring so if you remember, if we have our orthonormal basis, let's say I, then our measurement operators are simply, these would be our measurements. So this doesn't have to be the computational basis, this could be any basis. And here we have the Bell basis. So beta 0, 0. Beta 0, 1. 0, 0 minus, yeah. You need a 1, 1. And they're paired off. So it's absolutely clear. Okay, so here's an orthonormal basis. And we can measure this basis by simply putting a C naught here and Hadamard again. Here. And we can check that this indeed allows us to do measures in the computational basis. So let's see what happens. Let's see if that's true. So if we start off with some psi, which could be alpha 0, 0. So some state in a 2-qubit system, then we apply our C naught gate. That goes to that. And now we Hadamard it. So let's see if I can Hadamard it and group things together at the same time. So how do I get 0, 0? Well, I'm going to get it from here and here. Because when I Hadamard, oh no, here, sorry. When I Hadamard the first term here, this will go to a minus, which also has a 0 term. So this will be 0, 0 plus alpha 1, 1 divided by root 2, I guess. 0, 0. How do I get 0, 1? I'm going to get a 0, 1 here from the Hadamard here and also from here. So this would be both positive. And the 1 zeros are a 0, we're going to get a minus here. 1, 0, and that's also going to be, sorry, that's going to be a plus, because that's a plus. And then 0 and a minus there. Finally, the 1, 1s. That's going to give a minus, which is going to, a plus, which is going to give a 1, 1. So that's going to be 0, 1. And the other 1, 1 is going to come from here with a minus. Okay, so that's now applied the Hadamard, and conveniently I've done it so that now we have everything in its place, and it is wrong. That should be a 0, 1 according to my plus 1, 0. Yeah, this is not 0, 0 here because this second qubit doesn't change. So this is a 0, 1. The other one is coming from here, when this becomes a minus, that's what is plus 0, so that's plus 1, 0. Okay?
What we want to do is like map the Bell states to the subindices, or like say, right? Like map beta 0, 0 to 0, 0 with probability 1, or like, and then, so when we, like if we turn the beta, like if we start with something in the computational basis, sorry, in the Bell basis, then we would turn it into the same thing, but with the coefficients in the computational basis, or?
It's something like that. In fact, it wasn't clear to me exactly. They only, in Nielsen and Chuang, they give this as an example, and then they kind of scoot off and say, you know, what confused me was, why is this not this isn't how you get to the Bell basis, right? I mean, you get to the Bell basis by putting the Hadamard here and then the signal, as we just saw.
I think that they would want to invert it, right? It's like,
exactly, you need to invert it. So it's exactly that.
Like I thought, like if you have the psi with the coefficients like alpha 0, 0 times beta 0, 0 plus alpha 0, 1 times beta 0, 1, and then at the end of the circuit you would get alpha 0, 0 times 0, 0 plus alpha 0, 1 times ket 0, 1.
Yep.
So like, why are we starting with a vector, like a state in the computational basis? And like, wouldn't it be more clear, like the example started off with like defining the state in terms of the Bell basis, and then showing that at the end you get the same coefficients in the computational basis? Like, I don't get why we're like the way the example starts with psi defined in terms of the computational basis instead of the Bell basis. Like, does my question make sense?
Yeah. Okay, so what happens if you start from the Bell basis? You'll basically apply the inverse. So it's measuring in the Bell basis, yeah. Okay. Is that what your point is, isn't it?
Like, does this circuit turn beta 0, 0 into 0, 0 with probability 1? Or?
Let me finish what I was going to do.
Okay. Sorry. My bad.
Okay.
Yeah, sorry.
What does measuring in the Bell basis now mean? So if we the measurement with beta 0 is this, okay? That's the measurement operator. And if we apply it to this, if we apply it to psi, so if we now apply this to psi here, then we get 1/2 of alpha 0, 0 plus alpha 1, 1, and its conjugate, right? Yeah. So how do we do that with the... And of course, if we measure the computational basis, we measure 0, 0, we get the same thing. What Adrian is saying is that why don't we just start off with psi with respect to the Bell basis, apply the inverse, where the inverse he means the unitary transformation which takes you from the computational basis to the Bell basis. The inverse of that, put it here, and then clearly you'll get the same thing. That's true. Yeah. I think he's right. Yeah.
So then how does this example show you measuring in the Bell basis? Like, how are we met?
Well, theoretically, if we measure this in the Bell basis,
okay.
This is what we would get, right?
Okay, yeah. Now.
Practically, you see it now, right? I mean, if you measure 0, 0,
that means you got the thingy on the top. Yeah.
You've measured beta 0, 0.
Yeah.
Yeah, etc., etc. So I think, what it is if you have an n-qubit operator, you just put It's just this, isn't it?
Yeah, exactly. Right, and then you measure in the U basis.
Yeah. Agreed. Which is why you've got the mysterious, the H is now on the wrong side, if you like. Because in fact it's the inverse.
Yeah.
Muy bien. Yeah. Okay, I've just about got time to do something which yeah, I'm not, and I'm going to draw something up and then I'm going to leave it as an exercise, okay? So anyway, so we can see, I think we're all, yeah, so let me just write that down. So to measure, so suppose U is the change of basis matrix, basis from the computational basis to some orthonormal basis B, then this circuit will measure in the basis B. And if you want to prove Adrian will provide the proof for you. Yeah? Yeah, I think that makes total sense. And there's almost nothing to prove, right? Put the curvatures back and measure. Yeah. Goodness me, we still have quite a lot. So here's, so now we're going to start our quest to prove that the Hadamard C0 and the T gate are enough to, well, are a universal set if we allow ourselves some small error, because obviously the unitary transformations are over the complexes, so it's continuously. So we can never hope to find a discrete set of universal gates, but we can find a discrete set of universal gates up to an arbitrarily small error. Okay, so the first thing we're going to try and do is prove that you can implement the Toffoli gate with just the following gates. So our overall aim will be to prove we can approximate a simple qubit with H E to the I1. Well, no, hold on. I don't think we don't need that anymore yet because we've already got an arbitrary. Again. operation, because we've already broken down the unitary operation into topheles and single qubits. So now we're going to do the single qubits, which will then imply the arbitrary unitary operator. Given that we can do the toffele, which is what we're going to do now, okay? So we can do, so firstly we're going to prove, that the toffele gate can be implemented with these gates. Right. So let me just draw it up, and I will check a couple of things and leave the rest of it as a pleasant exercise for you guys before Tuesday. So, and then we don't have to do it again on Tuesday, we'll be done. So here we are, we have 13. We have 3 qubits, obviously, to implement our toffele. Let's get rid of that. And here goes. So we've got H, 1, 2. So C naught. Hermitian conjugate of T. Another C naught. T. C naught. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Almost there. 11, 12. Well, it's actually 14 because here we've got 2 T's. Now that, miraculously, implements the toffele. Are there any that we can just, so I mean, we've only got 8 things to check, but of course 8 times 14 is quite a lot. Don't particularly want to do that. I've written down here that 0, 0 something is obviously it's obvious. I think that's kind of true, right? So it is. Let's say it is evident that 0, 0 t goes to 0, 0 t. If you look down here, the C naughts aren't going to come into play because there's these first 2 bits are not set. So this T conjugate with T, I mean T is unitary. So this is the identity. This is the identity. H is Hermitian and unitary. So that's H is going to be the identity. And up here, this is the identity, and this is the identity. So the only thing that happens is this T up here, but this T up here on the first qubit, if it's set to 0, it's just 1, doesn't do anything to it. So I think it's evident, just about, that 0, 0 t goes to 0, 0 t. Any complaints? Okay, so let me just use the last few minutes just to see if I can calculate some more. So let me try and do 0, 1, 0 and see if I manage to get the fact that this should go to 0, 1, 0. So what we're saying is this is the topoly. Yeah, so this should be topoly. So we claim, okay, this is topoly. So 0, 1, 0 should go to 0, 1, 0. Let's see what happens. So this will be step 1, it will go to 0, 1 plus. This step 2 is now going to C naught, so this will be, what happens if you, so I've got the second one set, if I C naught a plus, what happens if I C naught a plus? Anybody? So recall that plus is that. So what happens if I C naught it?
Another plus.
It's another plus, so nothing. Right? It's an eigenvector of x, an eigenvalue 1. Now t conjugate to the third qubit. So now. So the first bit is going to be unaffected, so that's just going to go 0, 1, 0, but the 0, 1, 1 will get a factor here, so this will get an e to the I pi divided by 4 minus, this is t vector, 0, 1, 1. Okay? 4. That's right, isn't it? You will stop me if I go wrong, won't you? 4, nothing happens because this has got a 0 set here, so that's the same. 5, we now map it back to the t, so that goes back to how it was before, so that's back to 0, 1 plus. And now we do exactly the same as we did before, so 6 goes. I'm loath to rub out my tea. So I'm up to 6. I C naught it. So that again, nothing happens to the plus. 7 then gets is this again, but then nothing's going to happen here. So something happens. Oh, do you really want me to do this? Because okay, it goes to this again, but it's going to get mapped back again. Because nothing happens on 8. On 9, it gets mapped back again to 0, 1 plus. And then you apply the Hadamard to a plus, you go back to a 0. So on 10, it gets back to 0, 1, 0, which is what we wanted to prove. Actually, it wasn't too bad. I thought that was going to be worse. So we've got time to do one more, and then we'll call it a day. Anybody want to tell me what to do? Don't say 1, 1, 1, because that would be a lot. What should be the next easiest one? 1, 0. Oh, we've already done the 1, 0, 0. That should be fairly easy, right? So 1 goes to 1, 0 plus. 2, nothing happens. 3, it gets mapped to 1 over root 2, 1, 0, 0. 1. 4, it gets mapped to 1, 0, 1, 1, 0, 0. 5 gets mapped with a T. So 1 over root 2. So nothing happens here. Now we get it. Oh, so that's going to go back to how it was before now, because now I'm going to do a T bar back on that one. So that's 1, 0, 1. 1, 4, 1, 0, 0. 8 now. I mean, this is almost as bad as doing Gaussian elimination. I'm probably making a mistake as well. And now I've got to do a T bar to the first bit. Well, that does the second bit, but that doesn't do anything. And this T down here will get rid of that. So now I go to 1 over root 2, 1, 0 plus. So that's simply 1, 0 plus. That's 9. 10, it's going to
Without the root 2 now.
Sorry?
Without the root 2, like if you already put the plus, then.
Oh! I just put that there to see if anybody was still listening, Adrian. I'm pleased to discover that you still are. This now goes to 1, 1, 0, because I got a C0 and I had marked the last one. This 1 now gets the e to the minus I pi divided by 4, 1, 1, 0. 12 now gets that flipped back again to 1, 0, 0. And now we apply a T. This T, these two T's don't do anything. This T then puts it back to 13, 1, 0, 0. And we are done. We are back. Goodness me. I am looking at the recording of the board and it looks horrendous. So I will leave you as a fun exercise. So I've done 1, 2, 3, 4 of the 8. Okay, so that's not bad, done half of it. I'll leave the other half for you guys. And next time we will be proving the approximation. So we will be approximating quantum circuits. Yeah, we might get through it. We might get through it, in which case we will be able to do the exercises on the following Thursday before Easter, which would be great. I will send out a list of whose exercises sometime tomorrow. Okay? I shall stop the grabación. Do you have any